So let me see. Some of you made a mistake in. I'll post the solution manual in Moodle. Especially number one, I was a little bit serious with the grading. So number B, actually number C. Number C, if you missed something, you can easily lose 1 point there.
Yeah, that guy.
Yeah, I think I said that in class before. Yeah. So for any, actually for any, it can be 0,
Yeah.
it can be 1, like that. For
Okay.
any, yeah.
That's what got me. Forgot it could equal 0.
Yep, it can also be 0.
Yeah.
But anything else there was okay. Number 2, Alice, you made a. I don't know where you got those. What is your name? Alice?
Alicia.
Alicia. I don't know where you got those values.
I don't know where, because I solved it and then somehow copied, I actually, it looks like I just copied the numbers from the top
Oh, okay.
into my solutions.
Oh, geez.
Like, I actually went through and solved it, got the right answer, and then when I wrote solution, I wrote,
Okay, number 3C. So you actually multiply the matrix and the vector. It is not the vector and the matrix. So some of you made a simple mistake there, and then number four. No, number 4 is okay. Everyone was okay with that.
That one confused me for a bit because I first was like, is this augmented or not? Maybe
No,
something
actually, that one
wrong.
is not augmented matrix. It is
That's the assumption I made. And I'm
Yeah.
glad I made that assumption.
not. So I wrote to some of you that is not augmented matrix. Yeah,
and that's where I went wrong.
It's
Yeah,
completely different.
it is not. Yeah.
Yeah.
Yeah, if you just given the matrix like that, then it is not an augmented matrix. Number 5 is okay. Number 5, you can actually let x3 to be 0, and then you get those values there. Because I gave you a hint up there. Find the solution of the vector equation x1. So you can come and replace the value of x1, x2, and x3. And then number 6. Number 6 is okay, but I said you must include B1, B2, and B3. You need to include them there because you want to see whether it spans at 3. So you can let B to be equals to B1, B2, B3. And then number 10. Number 10 was the easiest. It's actually very simple to solve. So because you just look for, you can actually reduce directly, but since it is an application of homogeneous linear equation, you must include 0, 0, 0 for the matrix. And then number 8. Ethan, were you who was asking whether it can be 1-to-1 and onto? Was it you?
I think I made a comment where onto is 1-to-1, but 1-to-1 isn't always onto. You know,
Yeah, so
it's kind of
it
like
can-
square and rectangle thing.
So for number B, it is actually 1-to-1 and onto.
I forgot the definitions of those as I was going. I was like,
So
I think it's on.
for the
Yeah.
onto, we said it's have the pivot position in each of the row, and then for the
Yeah.
one-to-one, each of the
Columns.
column. Yeah,
Yeah, and that's what I couldn't remember which was.
Yeah, so it can be onto and one-to-one.
Mhm.
Yeah, so you
Okay.
can just say it's a bijection.
Yeah.
Then number 9. I was solving and I made a mistake by myself. So there is actually 2, 2, and then 1. 2, 2, 1. And that was it.
Mhm.
Say this is the easiest test of the.
This is the easiest actually. So make sure you, but anyway, it's I'm not threatening you guys. It's everything that we learn here is in your exams. So don't get worried. As long as you study.
Yeah. Next exam will have the matrix multiplication.
Yes, so next exam will be chapter 2.
Mhm.
Chapter 2. Okay, and the next exam will be on 15th of this month. Okay, so let's now look at the inverse of the square matrix. The inverse of the square matrix. So let's start by defining what the inverse means. So we start from 2.1. And this is the definition. So an n by n matrix A is called invertible matrix. If there is an n by n matrix B such that AB equals to IN, AB equals to IN, and also BA equals to IN. Also BA equals to IN. IN is the identity. So in this case, the matrix B is called the inverse of A, the inverse matrix actually, matrix of A. If A is not an invertible matrix, then we say that A is a singular matrix. If A is not an invertible matrix. Number 1.2. Okay, actually here it's 1.1 and then this is 1.2. Let's look at the theorem. If A is an invertible n by n matrix, then the inverse matrix A is unique. The inverse matrix A is unique. A is an invertible matrix and the n matrix. Then how can we show that the inverse is unique? So let's prove this. So we can let B and C to be inverse matrices of A. Let's B and C to be inverse matrices of A. Then that means then AB equals to what? Equals to IN. And also CA equals to IN. Also CA equals to IN. Then C is the same as CIN, right? C is the same as CIN. And this is also equals to this IN. We can replace this IN by AB. So CAB, right? So IN there is the same as AB there. Then this is also the same as CA, and then what? B. CA and then B. And then we said IN here is the same as, so this is also the same as IN, and then B. And then this is the same as what? B. So it shows that the inverse is unique. The inverse is unique. Now, let's look at the notation for the inverse, and that is 1.3, the notation. The inverse of sorry, I'm gonna start this one again. If A is an invertible, n by n, then we denote the inverse matrix of A, S, A, and then we put it like that. And then we put it like that. This is also, this is just the same as 1 over what? 1 over A. It's just the same as 1 over A. So that is the inverse. It's the same as 1 over A. Okay, let's look at first example. Example number 1. Show that B, which is equals to 2, 1, 3, negative 2, 1, negative 6, 1, negative 1, 4, is the inverse matrix of A, and this A is the same as negative 2, negative 7, negative 9, 2, 5, and 6, and then 1, 3, and 4. So show that B is the inverse of A. So what you need to do here is you need to check whether BA equals to AB equals to what? I, and then these are what? 3 by 3, I3. So the solution. So that is what you need to check. So when we multiply BA first, then it is 2, 1, 3, negative 2, 1, negative 6, 1, negative 1, 4. And then multiply by negative 2, negative 7, negative 9, 2, 5, 6, and then 1, 3, and then 4. So what you should get is the identity matrix. What you should get is the identity matrix. Let's see if the first one is giving us 1. 2 multiplied by negative 2 is negative 4, plus 2 multiplied by 1 and by 2 is 2. So negative 4 plus 2 is negative 2. And then 3 multiplied by 3 is 3. So -2 plus 3 is what? Let's see whether the next one here is 0. So 2 multiplied by -7 is -14 plus plus 5 is negative what? -9. And then the last one is 9 plus 9 is 0. So basically this is 0, 0, and then 0, 1, 0, 0, 0, 1. So to give you an identity matrix. Again, if you multiply AB, which is -2, -7, -9, and then 2, 5, and 6, 1, 3, and 4, multiplied by 2, 1, 3, -2, 1, -6, 1, -1, 4. What you get is the same, which is 1, 0, 0, 0, 1, 0, 0, 0, and then 1. So it shows that B is the inverse of the matrix A. Now, since AB equals to I3 and BA equals to I3 also, then B is the inverse matrix of what? Of A, the inverse matrix of A. Okay, let's look at 1.4, and this is the invertible 2 by 2 matrices. So we'll just take this one, we'll not prove it. You can check in the textbook. What you do first is you need to get the determinant. The determinant of a 2 by 2 matrix A, which is the same as A, B, C, and D, is we write as the determinant of A, which we also can write as A, like that. We can also write it like that, which is the same as you multiply the diagonal minus the other diagonal, which is the same as AD minus what? Minus CB. AD minus CB. So determinant of A can be written as, write it like that. Was AD, so AD minus CB. Now the inverse of A, then number one, if determinant of A is not equals to 0, if the determinant of A is not equals to 0, then A is an invertible matrix. And A inverse is written as 1 over determinant of A, determinant of A. And then what you do here is you interchange A and D there, so D, and then you put A here, and then you put the minus here, minus C and minus B. Okay. This is just similar to 1 over determinant of A here is AD minus CB, and then multiply by D minus B minus C, and then A. So that is the determinant and the inverse of a 2 by 2 matrix. Inverse of 2 by 2 matrix. Now, if number 2, if the determinant, if determinant of A equals 0, then A is what? A is a singular matrix. A is a singular matrix. You can look at the proof in your textbook. Any question up to that? Okay, let's look at example number 2. Let A be equals to 1, 2, 3, 4, and B equals to 1, -1, -1, and 2. Number A, let's find A inverse and B inverse. Let's find A inverse and B inverse. So what is our A inverse? Solution. So what we need to do is we need to get determinant of A, which is equals to what? 1 multiplied by 4 minus 3 multiplied by 2, right? Which is equals to 4 minus 6, which is equals to -1, -2. Determinant of B equals to 1 multiplied by 2 minus -1 multiplied by -1 there. And this is equals to 2 minus 1, right? And which is equals to what? 1, which is equals to 1. So that is the determinant. So now the inverse. So A inverse is equals to 1 all over determinant of A. And then we interchange those values there, which is 4 here, and then 1 here, and then we put the -3, and then -2 there, which is equals to 1 over -2, 4 minus 2 minus 3, 1. Which you can still write this one. We can still take -2 inside there, -1 over 2 inside, which would be what? Which would be -2, and then this one is 1. This one is 3 over 2, and then this one is -1 all over 2. Yeah. Yep.
Is that like the absolute value of A? One over absolute value, is that what that sign is, or what is that?
That is the determinant.
Is it also very similar to the magnitude of multiplying factors together, which is kind of like finding the absolute value of. Because it reminds me a lot of vector multiplication.
Yeah.
Yeah. But
For the vectors, actually determinant is basically I can say the magnitude of the matrix. Yeah.
yeah,
This I cannot say the size. Because the size is like 3 by 4, 5 by 6, like that. So let's just put it like that. Let's say it's a magnitude, something like that. So basically, if I write it like this, then it's this.
So it doesn't mean absolute value.
It doesn't.
although you use like the same notation.
I just wrote it here.
It's like a notation.
So you can write it like this, determinant of A, or you can put it like this. Yeah. So most of the time, people will just use that to write this like that. But you can also like input the determinant B or determinant.
It's kind of confusing because you can get a negative number from that, even though typically when you see those lines on your side, it's like you're always going to get a positive number. It's
Yeah, if it is,
Absolute
yeah, absolute is just the positive number. But the size of a vector is actually, it is a square equals to, or you can just say if it's a vector, the size of a vector, then I think it was like, if it is a 2 by 2, then it is 2 square plus 3 square, something like that, and then you get a square, right?
Right.
And then you just get that's the size of a vector. But here, this can be, the determinant can be negative, like for instance, this is -2. Yeah, so it can be positive or negative.
That's just because of the nature of vectors, how there's,
Yeah.
like, it's not scalar, it's two other things.
Yeah.
It's two things together.
So you can write it like this, or you can just put it as determinant of B. I usually like writing like this. Okay, for B inverse is the same as 1 over determinant of B, and then you interchange as well. 2 and then 1 here, and then the other ones you change 1 and 1. And this is the same as 1 over 1, and then 2, 1, 1, 1, which is the same as 2, 1, 1, 1. That is the inverse. Okay, number B. Find AB. Also find AB inverse, and also find A inverse, B inverse, and B inverse, A inverse. Let's find those ones. So AB, you just multiply the two matrices. So AB equals to 1, 2, 3, 4 multiplied by 1, -1, -1, 2, which is giving us what? So 1 minus 2 is -1, -1 plus 4 is 3, 3 minus 4 is -1, and then minus 3 plus 8 is what? 5. I hope that's. Yep. And then, so what is AB inverse? So AB inverse is, you just get the determinant of this. So then determinant of AB equals to what? Equals to -5 minus 3 multiplied by 1, which is equals to -5 plus 3, which is equals to -2. So the AB inverse is the same as 1 over 2, and then you do what? You switch this and that, which is 5, -1 here, and then here will be 1 and -3 there, right? Yeah. So that's AB inverse. Okay. Now, what is A inverse, B inverse? So you multiply the two of them here, A inverse and then B inverse. So A inverse, B inverse is the same as, we can use this 1 over -2, and then 4, -2, -3, and then 1 multiplied by this one, which is 2, 1, 1, 1, which is the same as, you can just factor out 1 over -2 there, and then you multiply these two matrices here. When you multiply this, then you get so let's multiply. So this and this is 8. 8 minus 2 is what? 6. That and that is 4. 4 minus 2 is 2. This and this is -6. -6 plus 1 is -5. And then this and that is 3. -3 plus 1 is -2. And basically this is the same as what? -3, right? And then -1, 5 over 2, and then 1. That is what you get. Okay. What about now the next one here? B inverse and then A inverse. get the inverse of that. So check B inverse and then A inverse here. So so you can write 2, 1, 1, 1 multiplied by, we can take this minus 2, 1, 3 over 2 minus 1 over 2 there. And what you should get here is basically minus 5 over 2, 3 over 2, minus 1 over 2, and then 1 over 2. That's what you should get. This B inverse A inverse is similar to this, and this can be what? Minus 5 over 2, 3 over 2, 1 over 2, minus here, and then 1 over 2. It should be similar to this, and they are similar. Okay. We'll see a theorem of that. Number C. Now let's find A transpose, and then inverse, and A inverse, and then you transpose. So A transpose is equals to 1, 2, and then 3, 4. A transpose, and then you do the inverse, is the same as doing what? Getting the determinant here, right? Determinant here is 4 minus 1. 4 minus x, which is minus 1 over 2. Oh, and then you do what? You switch that 4 and then 1, and then minus 2, and then minus 3, right? Okay, and then A inverse, we have the A inverse here, which is what? Which is this. So A inverse transpose is the same as A inverse, which is minus 2, 1, 3 over 2, minus 1 over 2, and then we do what? We transpose, which is the same as minus 2, 1 here, and then 3 over 2 there, and then minus 1 over 2. And this should be similar to this one. Should be similar, because this is equals to what? Minus 2, right? There is 3 over 2. There will be 1. And the last one here is minus 1 over 2. And you see they are similar. A transpose inverse. Any question? Our friend did not come today. So that is any question up to that? So let's write a theorem which is now proving what we just did as an example. 1.5. If we let A and B be invertible, n by n matrices, then number one, A inverse is an invertible matrix, and A inverse, and then you do the inverse of it, you will still get A. So these are actually similar to the transpose that you are doing. If you put the transpose and then you transpose again, then you still get the same You remember when I told you you can replace the T and the what? The inverse, right? Okay, so you can replace the A G with that inverse there. Number 2, A transpose is invertible matrix. And A transpose, and then you do the inverse, is similar to A inverse, and then you transpose. Just like the last example. Then number 3, AB is an invertible matrix. And AB inverse is the same as what? B inverse, A inverse. It should be, it is, this AB inverse is not equals to A inverse, B inverse. It is equal to B inverse, A inverse. So you can look at the proof from the textbook, but the proof is just similar to just proof from the example.
Got a quick question. So for number 2, every transposed matrix is invertible. Is that what it's stating first there?
Every transpose matrix is invertible.
Yeah, is that what it's saying? Like AT is
No.
reversible?
If a transpose is invertible.
Okay, if it is.
Yeah,
Okay.
if
gotcha.
it is actually invertible. If the transpose is not equal to 0,
All right.
then when you transpose it and get the inverse, it's similar to getting the inverse, then you transpose.
Okay.
So long as it is not it is invertible.
Mhm.
So long as it is invertible.
Okay.
Okay. Now, if you have a lot of matrices, like let's say, for example, let's look at theorem 1.6. If we have A1, A2, all the way to, let's say, AN, and all these are invertible n by n matrices, then the product A1, A2, all the way to AN is also invertible. N by n matrix. And the product, which is A1, A2, all the way to AN, and then you get the inverse, is similar to starting from the last one, which is AN inverse, AN minus 1 inverse, and then you continue like that until A2 inverse, and then what? A1 inverse. Just like AB inverse is equals to B inverse, A inverse. So you start from the last one. Okay, 1.7, the cancellation laws. The cancellation laws. If we let A, B, and C be matrices. Number 1, left cancellation law. If AB equals to AC is and A is invertible, then B equals to what? B equals to C. Number 2, right cancellation. If AC equals to BC and C is invertible, then A equals to B. equals to B. So this you can actually prove just from the definition of the inverse. So we can prove this one simply. So to prove the first one, number one, if we have our A B equals to AC, AB equals to AC, then if we multiply the right, the left, sorry, left cancellation is multiply the left by the inverse. If we multiply the left by the inverse, A, B, you do it in the other side, multiply the left by the inverse, A, C. And this is the same as what? INB equals to INC. And then B is equals to what? C. B is equals to C. Also, number two, right cancellation. If you have AC equals to BC, then at the right you multiply by the C inverse. So ACC inverse equals to BCC inverse. And this is the same as AIN equals to BIN. And this is the same as A equals to what? Equals to B. Equals to B. So those are the left and the right cancellation. Okay, 1.8 theorem. If A is an invertible n by n matrix, and B, the vector B, is a vector in Rn, then the matrix equation AX equals to B has a unique solution. X equals to A inverse B. It's a unique solution. So we actually get this one from the left cancellation. From the left cancellation. So to prove these, then you can look at the proof from the textbook, but if A is an invertible n by n matrix, then using the left cancellation there, if we have A inverse equals to B, then if you use the left cancellation, then you multiply by the inverse from the left, A inverse A, X equals to, you do it in both sides, A inverse B, like that. And this will be IN X equals to A inverse B. And this is the same as what? X equals to what? A inverse and then B. So when you want to get the values of X, you want to get a solution, then you can just write the coefficient. A can be the coefficient matrix. B are the constants, the constant terms. The X are the values that we're looking for. So you can just get the inverse and then you multiply by the constant terms there. So we'll do this. We'll do an example of this. Just example number 3. Example number 3. So the following. linear system. We have x1 plus 2x2 equals to 4, 3x1 plus 4x2 equals to 6. Find the values of x1 and x2. So we can write the matrix equation of that. So the solution. So write A to be equals to what? 1, 2, 3, and 4. Now B to be equals to 4 and what? 6. Then the matrix equation is what? AX equals to what? B. X equals to B. So what do you need to do? Then our X there is equals to A inverse what? B. So we need to get the inverse of A. So we get the determinant of A, which is equals to 4 minus 6, which is equals to minus 2. And then A inverse is equals to 4, 1. And then minus 3, minus 2, 1 over 2 there. 2 there. So basically our X equals to A inverse, which is minus 1 over 2, 4, minus 2, minus 3, 1, multiplied by 4, 6 there. And what you should get is minus 2 and 1. Minus 2 and 3. So then x1 equals minus 2 and x2 equals to 3. Any question up to there?
So would you get the same answer if you just like, did the matrix into reduced echelon form?
Yep, you'll get the same one.
So this is just a different way of doing it.
Yeah, you can use this. You can get the inverse, and then you multiply with the vector, or you can just row reduce. So it's either way.
So is there a time when you want to use one or the other? Or does it just depend on?
So to use the other one if it is a 3 by 3, because for a 3 by 3 matrix, getting the inverse can be so tedious. Yeah. So for the 2 by 2 matrix, it's easy. You can use this one. But for the 3 by 3, you can actually use the other one. Yeah. But I'll show you how to get inverse of 3 by 3. Very easy. Okay. Any other question? And your question is just coming from this 1.9. This is theorem. If A is an invertible n by n matrix, then A can be row reduced to IN. So A can be row reduced to IN. So you can row reduce it and row reduce this one. And what you get finally here is the identity matrix. So basically you can put it in augmented matrix form, right? And then what you would reduce here, so long as it is invertible. For this one, for A to be invertible, then Once you roll reduce this, then you get the identity matrix. If it is not invertible, then you will not get the identity matrix. As long as it's a what? A square matrix. A square matrix. If it is not a square matrix, of course, you will not get an identity matrix because there is a row or the column which would have a free variable. Okay, any question up to that? All right, if there is no question, then let's.
So for the determinant, if it gets larger, is it basically just the same for,
If it gets to.
so like, let's say you had a 4x4,
Mhm.
okay?
Mhm.
So then is it all of the things on one diagonal?
Yeah, so I will show you how to get the determinant
Okay.
if it's a 3x3. So there is something we call the cofactors.
Okay,
So we'll use the cofactors method
Okay.
to get the determinant.
so what we've done so far only works for a 2x2.
2x2, yes. So we'll use the cofactors. So you reduce it to a 2x2. So you multiply by factor. I will just show you. Don't worry.
Okay,
Yeah, it's coming. All right, let's now come to the next section here, which is called an algorithm. For finding the inverse matrix. The algorithm for finding the inverse matrix. Okay, so let's define something here, which I think we defined the elementary matrices. Elementary matrices. An elementary matrix is a matrix that is obtained by applying a single elementary row operation. To an identity matrix. An elementary matrix. So we get that one by applying the row, the elementary row operations. You remember the elementary row operations that we had? You can switch, you can multiply by a constant, or you can add the constant on the rows when you're reducing. Okay, we will do an example on this. So let's take example number 4. Example number 4. If we let A to be equals to A, B, C, D, E, F, and we took I3, it is 1, 0, 0, 0, 1, 0, 0, 0, and then 1. Then write E for an elementary matrix. Let's write E for the elementary matrix. Now, if we take this, let's take the row operation. And then let's take our E here, which means E is the elementary matrix, which you get by doing the elementary row operation. And then let's take this one as E, and then we multiply by this A here. And then let's get the E inverse. And then let's get the inverse row operation. So let's make a table. Okay, now if we switch, let's switch R2 and R3. Let's switch R2 and R3, R2 and R3 from this identity matrix. Then our elementary matrix here will be what? We switch R2 and R3, which will be 1, 0, 0, and then 0, 0, and then 1, 0, 1, and 1. So that is our elementary matrix by switching. Switch R2 and R3. Now, when we multiply this elementary matrix and this A, what do we get? E and A. So 1 and 0, we get A. 1 and A, you get A. The others will be zeros. 1 and B, we get B. The others are zeros. 0 and A, we get 0. 0 and C, we get 0. 0 and E, we get our E here. Our E there. 0 and that. So we get our D there. And then finally, our C and D there. C and D. Okay. If you multiply this elementary by A, so this and that will be A, and the others are zeros. This and this will be B, and others are zeros. This and this will be 0, that and that will be 0, and then the last one is C, is E, which is this. And then this and this will be 0, that and that will be 0, this and this will be F. Writing my own things. F. This is F. That is F. And the others come down here. So what do you see from here? It's like doing what? Just like yeah. Okay, now the inverse here is the same. The inverse will just be the same. The inverse of E inverse here will just be the same. So if you switch or you do anything, the inverse will not change. 1, 0, 0, 0, 0, 1, 0, 1, 0. The inverse will still be the same. So the inverse row operation, if you still remember, was the same thing, R2 and R3. Just switching the inverse row operation. R2 and R3. Now, if we do another row operation here, if we take R3 and then to get the new R3, we multiply by -4 R3. We multiply R3 by -4 to get the new R3 there. So our elementary matrix here will now be 1, 0, 0, 0, 1, 0, 0, 0, and -1, and -4. Now, if we multiply these and our elementary matrix there and our matrix there, then what you get is 1, 0, 0. What am I writing? What you get is actually A. The next one is what? B, right? 0, 0. This and this will be C. The others are 0. 0, that, and that will be D, and the others are zeros. And then the last one is 0, 0, 0, 0, and then -4E. 0, 0, 0, 0, -4F. See, it's just similar to multiplying by what? That matches over there by -4. Now, the inverse here, the inverse of this elementary matrix here, the inverse here will just be 1, 0, 0, 0, 1, 0, 0, 0, -1/4. That will be the inverse. And if you remember the inverse, if it is R3, the inverse is -1/4 R3. Right? -1/4 R3. Our inverse operation. Okay. Now, if we take the last one, if we take R1 and then R1 minus 3 R3, we want to get the new R1. So let's just subtract R1 to get the new R1 by minus R3. Then the elementary matrix here will be 1, 0, minus 3, 0, 1, 0, 0, 0, 1. So that will be our elementary matrix. Check this, the new R1, which is R1 minus 3. So you get this one. Now, when you multiply this and now this A, what do you get? So 1 and A is A, right? And then the next one is 0. The last one is minus what? Minus 3E. Minus 3E. 1 and B is B. The last one is minus 3F. And then the others will just be the same thing. The others will just be E, C, C, and then D, and then the last one is E, and then F. So that would just be. So our inverse in this case of E is just changing the sign, which is 1, 0, 3, 0, 1, 0, 0, 0, 1. Changing the sign. And R1 is just R1 plus what? 3 R3. Okay, now let's write the properties. 2.3 properties of elementary matrices. So what happens for the elementary matrices? Let's write the properties. Number 1, every elementary matrix is an invertible matrix. As we can see, we can actually get the inverse. Number 2, the inverse matrix of an elementary matrix is an elementary same type. It's an elementary matrix of the same type. And then finally, number 3. If A is an M by N matrix and E is an M by M matrix, M elementary matrix, that is obtained by applying an elementary row operation to IM, then EA can be obtained by applying the same elementary row operation on A. We have just seen that one from that example. Just find it by applying the same thing on the matrix A. So the next theorem here will show us how now we can get the identity matrix, or we can get the inverse by just applying the elementary row operations. And this is just like this. So theorem, an N by N matrix A is invertible if and only if A can be row reduced to I. So this is just like a theorem that we just wrote about, but here we use the elementary row operations. Now, if we prove this, if we have a so we can find sequences of elementary row operation. We can put as operation 1, operation 2, all the way to operation R, such that we have our A, and then we do the operation 1, elementary operation on E1. Then when we multiply by that E1 by A, then it is just similar to changing or using the elementary operations on what? On A. And this can also continue like that, operation 2, and then we multiply by elementary operation. You can take this one as E2. Then this E2 and E1 and A. And then if you continue like that until, let's say, operation R minus 1 here, and then ER here minus 1, then ER minus 1, you continue like that, and then E2, E1, and then A. And then the last one here, operation R, and then ER here. Then what you get is ER minus 1, you continue like that, E2, E1, and then if you multiply by our A here, then what you get is the identity matrix I. Identity matrix I. Similarly, you can just switch it. If you have our, if we have our IN here, and then if you have our identity here, and then we do the operation 1, and then we multiply by I1 there, then it is the same as getting I1 multiplied by N, which is the same as I1. If you continue like that, operation 2, E2 here, then it will be E2 and then E1 here. If you continue like that until now, the last one, let's say ER minus 1, and then E2, E1 here, then what you get is an inverse. So what you get is so therefore, in this case, then when we will be doing that, we'll be trying to get the identity matrix of a 3 by 3 matrix. Then what you do is you take the matrix, which is, let's say, a matrix 3 by 3, which is A, and then you add here an identity matrix here, which is 1, 0, 0, like that, up to the last one here. Then you reduce. You reduce up to the point that this side is an identity matrix. Then what you get here, once you reduce the whole of it, then what you get here is the inverse of a 3 by 3 matrix. So you actually put this 3 by 3 matrix here and the identity matrix here, and then you reduce it up to the point that you get an identity matrix here. So that identity matrix that you get here, so what you get here, the values that you get here are the inverse of this matrix, the inverse of the matrix. So this is what this theorem means. So therefore, this will lead us to this theorem, which is actually, this is an 2.4, an algorithm for the inverse matrix. And in this case, then if we let A be an n by n matrix, row reduce the n by 2n here matrix, which is A and then in there, to the reduced echelon form, to the reduced echelon form. And in this case, number 1, then if the left n by n matrix is identity matrix, which is In, then A is an invertible matrix. And the right n by n matrix is A inverse. Is A inverse. Number 2, if the left is not, if the left n by n matrix is not In, then A is what? Singular matrix. A is singular matrix. So let's look what it means. We'll look at an example of this. And the example will just be how to get, so I can just give you the example, how to get the inverse of 3 matches using this algorithm. So this should be like this. So you can find example number 5. Find inverse matrix of A, which is equals to 1, -2, 1, 4, -7, 3, -2, 6, -3. So what you just do here is you just write 1, -2, 1, 4, -7, 3, -2, 6, -3, and then you add the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And then you do what? You reduce this one. So you reduce up to the point that at the left, it is giving you the identity matrix. Then here, where there was identity matrix is now the inverse. If the left is the identity matrix. If it is not, then it is singular. It's singular matrix. If there is no question, then we can meet on Monday. All right, you too. You too.